Okay, hello everybody. This is our project on AI-driven soccer analysis using computer vision. I'm Tanner Cellio, and this is Adrian Manchado. And by day, we are computer science majors here at the Milwaukee School of Engineering. But by night, we are part of the MSOE men's soccer team. So we have this passion for computer science and this passion for soccer, and we want to combine these passions in order to solve a problem that we experience every day. And that problem is Rob Harrington. This is MSOE men's soccer coach Rob Harrington, and he is at the root of all of our problems. But we did not bring Coach all the way down here just to make fun of him. We actually developed this system in order to help him. You see, Coach has great intuition about the game of soccer. He's been around the game longer than I've been alive. But he isn't a supercomputer. He has limited memory, and he has limited time. So we want to help Coach in two major ways. One, we want to help answer complex questions that Coach can't answer himself. And two, we want to help provide quantitative data in order to back Coach's intuitions. So we do this by introducing Coach to Roscoe AI. Roscoe is going to represent the system that we have created. So there's two main challenges with helping Roscoe. And the first is getting Roscoe to understand what is the game of soccer. Because when you and I look at this image, we can understand what the players are, what the referee is, what the ball is. But when Roscoe looks at this image, all he sees are pixels on a screen that he doesn't understand. So we want to teach Roscoe three main components. The first are the players, then what teams those players are a part of, and then the ball. So starting with the players, how can we get Roscoe to understand that this grouping of pixels is what we identify as a soccer player? Well, it comes down to helping Roscoe understand and recognize the patterns of the pixels within the image. So we leverage an object detection model called YOLO. YOLO uses a convolutional neural network architecture in order to detect lines, edges, and shapes within the image. And by doing this, Roscoe is able to understand and recognize, hey, this group of pixels is what we call a soccer player. And after being able to identify a soccer player, we need to group them with their respective team. So we do this by using their jersey color, right? The jersey is just a bunch of pixels, and each pixel has a color. So if we can take the average color for all those pixels, then we can get the jersey color. From there, we use a technique called clustering. This helps us group similar jersey colors with other similar jersey colors in order to form two distinct teams. Another bonus feature of this is easy outlier detection. So if we have a player with an average jersey color of bright yellow, we are able to understand that this is not actually a player and identify this as the referee. So everything's perfect, right? We're ready to go? Well, not exactly, because Roscoe's trained on YOLO, but YOLO has no memory. So YOLO only operates on one frame at a time. In order for Roscoe to understand all the players, he needs to be able to track them in a time series. You see, when you and I look at these two frames, we can easily understand that the players at the bottom correspond to the same player. But Roscoe, he does not inherently understand that the player in frame A corresponds to the player in frame B. So we need to give Roscoe a memory. And we do this by using SAM2. SAM2 is a segmentation and tracking model that uses a memory component. Think of this memory component like a rolling history of all the past frames, used for lookup and comparison during the tracking process. So there's two main things we care about within this memory component. One is the appearance of the player, and one is the location of the player. And using these two features, we are able to link the same player across sequential frames. And when we do this for every player, we are able to assign every player a unique player ID. Think of this player ID like a jersey number in sports, right? One number that allows Roscoe to track that player for the same player throughout the duration of the video. So now, the ball, right? The ball is difficult because it's so small and it moves at such a high pace. It can often be fully or partially hidden behind players. So we use the same approach of using an object detection model called YOLO and using its convolutional neural network architecture to recognize the patterns of the pixels. But we need to help Roscoe a little bit more. So we give Roscoe some binoculars. And this represents giving Roscoe more samples of data in order for Roscoe to better understand the patterns of the pixels and understand, hey, this group of pixels is actually a soccer ball, and to be able to identify it. So now, let's put Roscoe to work. We give Roscoe this frame, and he's able to identify and put a bounding box around the ball. And then we give Dang it, Roscoe. Well, then we give Roscoe this frame, and he's able to find the ball again. So Roscoe, like us, isn't perfect. He can't find the ball in every image. So we need to help Roscoe be able to make an educated guess of where the ball will be in certain frames where it's not found. So we use something called a Kalman filter. Think of this like giving Roscoe intuition, right? Because we have the frame before and we have the frame after, then we can make an educated prediction using features like velocity and trajectory for certain frames where the ball isn't found. Now we don't rely on Roscoe having perfect vision. Instead, we give him intuition.
So now we have all the entities in a soccer game. So we are ready to measure real distances and get some insight from our games. Well, not really. Roscoe tries to measure two lines that are supposed to have the same length, and clearly they are different. This is because in an image, the objects that are closer to you are going to look way bigger than ones that are farther from you. As well, we have another problem. Our camera moves from left to right, zooms in, zooms out. This creates different dimensions for our soccer field, and that will make us that our field is going to be different. So how are we going to solve this problem? Well, we created a CNN model that is able to pick up key points in an image of a soccer field. This will give Roscoe different landmarks that is able to utilize in order to know where is it looking at any point in a video. So how we can actually use these key points in order to map to a 2D dimension to measure real-life distances. So what we use is a technique called homography that finds the ratio between the two images, 3D and 2D space, and now we can map any points in a 3D space into a 2D space. So let's see how this works. We have an image in 3D space, we have all the players, and we can apply homography, and now we have a bird's eye view in which we can track real distances and follow all the players across the frame. So if we put all the tools together, we have something like this, in which we can track players, assign them into teams, track the ball, and track them in the 3D space and the 2D space. So if we rewire all this Roscoe knowledge that we have, now he's ready to give us some meaningful insights. Maybe not that meaningful. But this opens a world of possibilities for us. Now we're able to track individual metrics such as speed, distance covered, or team insights such as possession or unexplored areas. For example, we can get a heat map of one of our players or the top 7 players with the most distance covered. So let's see how this works in real life. Now, in the top right, you have the changing possession for each of the teams, and then for each of the players, you have the speed and the distance that they've covered. This is cool, but how is this actually going to help Rob? How are we going to answer the question that he has? Well, one of the problems last season was we had a lot of injuries. We have more than 20 guys out of the field. And fatigue has been shown as one of the main injury sources. We can use measures like distance or sprints in order to track this fatigue. Professional teams have claimed that they've reduced by 1/3 the injuries using similar analysis. This would represent 6 injuries for our team. That can make the difference between winning and losing. But we are not really a professional team. We're a D3 soccer program, and we don't have really expensive hardware. We don't have a full team of data scientists, and we don't have multi-cameras that can capture every inch of the soccer game. We only have a single camera. We have Roscoe, but we have something they don't have. We have Rosie. What Rosie allows us is to train and run in inference 4 different key models that give us the insights like a professional team could do without having to spend thousands of dollars in expensive tracking equipment. But we have one concern. Roscoe has been telling me recently he's more into basketball rather than into soccer. So this pattern could be easily applied into basketball too. The only thing that we will need to do is retrain our key point detection model into a basketball data set and recalculate our stats adapted to this domain. So now, Roscoe is ready to coach. Hopefully, he will help us keep having moments like this, like last season when we became tournament championship. Thank you so much to everyone. As you can see, we're a team in and out the field. So we are going to open now for questions.
Great to see the great team spirit. I think this work is really interesting in that you're able to extract a lot of important metrics from video when it simplifies a process that I think could be really important and impactful. I guess I'm I'm wondering how, like, what sorts of insights can you pull from that? I think you covered, some ideas, but those are like first order metrics, like, if you track a player, how long are they on the field? It'd be interesting to see, like, how does that correlate to injury, as an example. And then other things that I'm sure your coach, Rob, would care about, like points. Have you had any thought about how you would apply these metrics to some of those other areas of analysis, or what other data you might need in order to do so?
Yeah, these are like the next data science project we want to apply. I was actually talking with Rob the other day on Saturday, saying like, which areas can make our team better. So one of the things could be, for example, if we are not getting the ball to a top left corner of the field, maybe there is a pattern behind him. He reviews the games like 3 times for each of the games. So if when he goes and reviews the games, he's able to see, we are not getting the ball to the left side. Why is this happening? And then we can identify, this player is not moving at the way he should. Or for example, we can create potential matchups that benefit from us. For example, we can identify and match our fastest player with the slower player of their team. That really creates a mismatch that can give us some potential advantage over other teams.
Yeah, I can add on that a little bit if I can find my slide. Okay, so one, we can do analysis on our team, but another idea we had is we can do analysis on the other team. So what if we could get their top players, speed-wise, and match our top players against their slowest players? Like, we had one of the fastest guys on the soccer field. Let's match him with their slowest defender to create that favorable matchup. We can identify their playmakers. We can get possession for each player. So who on the other team is being a key playmaker, and how can we shut them down? We can identify fatigue, which we talked about. Arsenal Football Club, professional club, they found there were 2 major factors: the amount of sprints that a player is doing, and then the distance covered. We can track both those metrics, so how can we use that in order to reduce the amount of injuries we have because of overtraining? These are just some examples. Yeah, I think there's a lot.
I hope your coach, Rob, doesn't take away from that. Everybody just needs to run slower.
Yeah. and then another thought that we have, what if we could have a database for all of the teams of the conference or all of the teams across the nation and plug it into a website that he could actually use, for example, with an AI agent. We already have a website that we are already tracking all of the stats from our practices, and maybe we could have a section in which we plug in a database in which he is able to ask questions and say, we are facing this opponent. Who's the player who is the most creative? We can have one of the sections here. Is this some future work that we're planning to implement? And that would make his life, I believe, much easier.
I guess I had one second question. You mentioned that you use both YOLO and SAM2. I'm curious why that was. What was insufficient about SAM2?
Yeah, I can talk about this. So SAM2, super powerful model, is pretty new, so we want to test it out. Now, SAM2 needs to be prompted, right? So YOLO provides that initial prompt. We take YOLO, and then YOLO works really fast, works in real time. So we run it through the first frame in a video. And through that first frame, it provides us bounding boxes. We take the center point of these bounding boxes, and then SAM2 is able to be prompted by a point. From there, SAM2 prompts all the players and tracks them continuously.
Smart soccer team. We must be the only ones in the conference that knows time series. Mm-hmm. But so if you keep going forward with this, when do we fire Coach Rob?
Look at him back there, bro.
He is back there, actually. I don't know. Maybe that's a conversation you guys have. No, I think he provides really something meaningful about the game. Yeah. Sorry. Okay, sorry.
This? Yeah, it's working. Okay. So I thought you're when you came to my office a while back and showed me this, Adrian, I thought this was super cool, right? You might remember that. I thought it was super cool. And I think now that I've heard it more like fleshed out, I think the idea of trying to, give endow the looker, right, with some kind of memory so you can track individual players, it's really neat, right? It's a really neat idea. It also seems like it's a pretty important thing for some of the downstream things you'd like to use this for, right? You need to be able to know that this player is this player frame on frame on frame, right? I'm just wondering, I'm wondering two things, I guess. First of all, I'm wondering if there are certain things that could happen in game that could complicate your ability to do that, like clumping, right? For example, where maybe players would accidentally get like switched, their IDs would get switched or something. And then second, kind of more generally, I'm wondering like what things you might have done to validate, right, or measure, right, the effectiveness of what you put together.
Yeah. Yeah, I can talk about this. So the thing you're talking about, two major problems with SAM2, right? Two limitations that it has. One is when a player leaves the frame and then comes back onto the frame, SAM2 isn't able to pick them up. So when we panel that can be a problem. The other thing is clusters, like you talked about. That's a big problem in sports analytics for computer vision, because when two players overlap, it's called an occlusion, and oftentimes, well, not often, but every once in a while, the SAM2 will track one player with both IDs. So it's a great question. We have we have kind of a solution for it. We didn't get to talk about it due to the time constraint. But what you do, so I mentioned you prompt SAM2 with YOLO, right? And then YOLO is able to identify like the amount of players. So we can so with SAM2, we know when a player, one, goes off the screen because we lose their player ID. And then two, using IOU, which is just a degree of overlap, we can tell when two players are being followed by the same player IDs because they have an IOU of like 99%. So we know when SAM2 is messed up. So what we do is on those frames where we know it's messed up, we re-prompt using YOLO just the specific player that isn't prompt anymore, and then we do another instance of SAM2 and run it continuously through the rest of the video for that. So if that makes sense, that solves the problem of the occlusions. Problem of the player leaving the frame is we just have to use YOLO on the continuous frames until the player comes back. And then we re-segment and follow that player continuously through the video. But yeah, like for example, I don't know if you can see, frame 30, that player down in the bottom left. Frame 60, he leaves. And then frame 180, he comes back. Just a demonstration of that problem that we're facing.
Excellent. Thank you so much.